Morning. All right, so sorry about the technology issues. Let's get through lesson 442. Okay, so before we start, I'm going to do a quick review of where you guys should be at, and this should all be pretty familiar. You guys should be able to find critical numbers. Okay, and we do that by f prime 0 or f prime undefined. Okay, that's how we find critical numbers of the first derivative. And then what we do is we have the strategy where you draw a f prime line. And what you do is you put those critical numbers, okay, right here, whether there's 2 or 10, it doesn't matter. And then we analyze these intervals around them because at those places, this happened, right? And so we're trying to figure out where is this increasing, decreasing, relative max, relative min. And we have all those definitions. The function is increasing when f prime is positive. It's decreasing when f prime is negative. We have our relative max where I'm going uphill to downhill, and a relative min where I'm going downhill to uphill. Okay. And all of this, you guys, is the first derivative. Okay. And what's going to happen in 442 in the second part of this section is that we just come down here and we're going to analyze the second derivative. And we don't really know yet what that tells us. Okay, but the process is exactly the same, right? Just different definitions because we're dealing with a different derivative. Okay, so we're again going to find critical numbers, but it's going to be of the second derivative. Where is that 0 and where is that undefined? We're still going to do our f double prime line, and we're going to put in these critical numbers, and we're still going to analyze the intervals around them, just like we did before. Okay, so what's up with the second derivative? Well, the second derivative, okay, talks about, concavity. Okay, and concavity is where, right here, this thing is a bowl pointing down. So we call this concave down. And right here, right, it has turned and now it seems like it's pointing up. So we call that concave up. And that's what the second derivative tells us. Whenever the function is concave up, that definition is that the second derivative is positive. So up here, increasing the first derivative, concave up, the second derivative is positive. Okay, f is concave down when the second derivative is negative. And so, logically, right, we're concave down here, we're concave up here. There must be some point where it changes from concave down to concave up, and we call that a point of inflection. Okay, point of inflection. You can abbreviate it on the exam, POI. And our definition of point of inflection is simply that f double prime changes sign. Right? Up here, I cared whether it went positive to negative because that was a relative max, uphill to downhill. And downhill to uphill was a relative min. Concavity changing from down to up or up to down, I don't care. You have a change in inflection, right? A point of inflection where the concavity will change. Okay. And so this is, these are our new definitions here, and that's all we're going to work with on these examples on the notes. Okay. I saved some paper and didn't print out the notes. I'm just going to write the functions down. But if you guys have the notes, you can just fill in. Okay. So this first example, okay, asks us to do a couple different things, but let me just write the function down. You've got this function. It's a polynomial. Nothing tricky with polynomials. They're great. They're smooth. There's no undefined values. And this is asking us to find relative extrema or local extrema. I'm not going to do that, okay, because I want to focus on these new definitions. So I want to find three things. I want to find where is this thing concave up, concave down, and any points of inflection. Okay. All right, so we do that just like we talked about. Instead of the first derivative, we're going to take the second. So you take the first derivative to get 3x squared minus 12x plus 9, which would give you the ability to analyze relative max and mins increasing and decreasing. If you take the second derivative, you get 6x minus 12. Okay, and the second derivative will tell us all of these things. And so the game is the same. We're going to set that equal to 0 because it's clearly never undefined. and you solve that to get x equals 2. And so x equals 2 is our critical number for the second derivative, making this guy, right, a possible point of inflection. We don't know. How do we find out? Same analysis, second derivative line with that one value right there, and then analyzing what's happening around it. Well, if I plug in 100, right here, I'm definitely going to get a positive number. And if I plug in negative 100, it's definitely going to be negative. Okay, and so we can report out now all these things. So we can say this thing is concave up, where concave up by definition is right there, from 2 forever, since f double prime is positive. Okay, it's going to be concave down from negative infinity up to 2, since the second derivative is negative. Okay, and then because we have this change, right, this is concave down, so it's pointing down, and then it's 0, there is no concavity, and now it's up, you have a point of inflection at that x value, right there, since f double prime changes sign. Okay, all right, so concavity, right, is another way to say that is it's increasing at an increasing rate. Okay, so let me just again talk real quickly about what that means. So you guys have a function like this. Hopefully you can tell that this guy is concave up. Okay, so what does that mean? Well, if this is your function, okay, f, right here, we know that f prime is positive, right? The slope of a tangent line is positive. Right here, f prime is also positive. But we can see that if this slope was like 1, now we have a slope of 2 or 3. And so a concave up function will have an increasing first derivative. Okay, so it's increasing at an increasing rate. It's kind of a mouthful. All right, the second example, you could have an undefined x value for the second derivative. So if you start with a function x to the 5/3, okay, let's go through our derivatives. Our first derivative would be 5/3 x to 1 smaller. Since we're asking about concavity and points of inflection, you have to go again to get the second derivative, which would be 2/3 times 5/3 or 10/9 x to 1 smaller, which is negative 1/3. And if you simplify that, you get 10 over 9x to the 1/3. So that's our second derivative. You got to check, where is that thing equal to 0? Never, right? We talked a lot about this. A fraction will be 0 only when the top or the numerator is 0, and that's not going to happen because there's no variable. But if you check where is it undefined, that happens when x is 0, right? A fraction will be undefined when the denominator is 0, and that denominator is going to be 0 when x is 0. Okay, so we have our critical number. You can then check around it and figure out concavity. Well, to the right, if I plug in 100, that's just going to be a positive number. You can take the cube root of 100. If I plug in a negative number, remember, you guys, you can take the cube root of negative 8. It's negative 2. Negative 2 times negative 2 times negative 2. And so plugging in a negative number will create a negative denominator. And so positive divided by negative would be negative. So function, again, concave down to up. So yes, there is a point of inflection at that x value since f double prime changes sign. Same justification every time. If you don't put it, you don't get credit on the AP exam or on tests that I give. Okay, there is some graphing on the second page of the notes that you can look over if you're confused on any of those definitions. Definitely ask me in the Zoom today. All right, guys.